Alright, hello and welcome. Today is Monday, March 30th. Another edition of Online AP Physics 1. People are still waking up, it seems, or their numbers are a little low for a Monday. I guess it is a Monday, but even then. Today you want to pull up your Unit 8 tippers number 9, the last tippers. We're kind of nearing the end of everything. So this is the last tippers assignment. Is it? Wait, I can't remember. I think is there a 10? I don't think so. I think this is the last one. We'll go over the tippers today, and then take a look at the extra practice problems. There are some classic physics problems in there that you should do. Prep yourself for the quiz that is coming up on Wednesday, and then we'll shelf off circuits after that. Remember, Friday there's no school. We are observing Cesar Chavez Day on Friday, and then the following week, next week, we have our spring break. So classes for the next 4 days, and then spring break technically starts on Friday, this Friday. And then we will come back on the 13th of April for 3 more weeks of online classes. Currently we're closed until May 1st, and then hopefully we will finally return May 4th. Alright, so let us see now. Let's see. Let's pull up tippers number 8. No, sorry, tippers number 9. Tippers number 9. Do I have it up? Yes, I do have it up. Good. And I'll just read the code so you know which one I'm talking about. We are starting with number D2 RT09. D2 RT09. In D2 RT09 we have the following. All of the bulbs in the circuit below are identical, as are all of the batteries, and it gives you 3 different circuits, and it says for the 2 items below, rank the current measured by the ammeter. Alright, anyway, a few things that we have to note is how do we make measurements in a circuit. Of course, we use a multimeter, ammeter, voltmeter, ohmmeter, etc. But it's also how they are connected in the circuit. Remember that ammeters are connected in series. Okay, and that's because elements that are in series have the same current. So when you put the same current rushing through the ammeter is able to measure that current. So in essence, if I had a battery, an ammeter here, or later, it doesn't matter if it's at the front or the back. Okay, we can say, this ammeter is in series with the resistor R1. And therefore the ammeter and the resistor will get the same current. So that's why you want to make sure your ammeter is in series with your circuit element that you're trying to measure. Whereas a voltmeter is connected in parallel. Connected in parallel. Okay. Well, we know that when resistors are in parallel, they have the same voltage. So let's say we have our battery and resistor. Okay, if I want to measure it, I'm going to put the voltmeter in parallel with the resistor. That way R1 and the voltmeter, remember, circle with a V is voltmeter. Circle with a V. And the voltmeter will have the same voltage as R1. Okay, so knowing that, let's go and take a look at the actual circuits. And the first one, D2RTO9, we have A, which is battery, ammeter, and then one resistor. Technically, it's a light bulb. Okay, and the resistance of each are the same. In B, we have two in parallel. Oh, ammeters over here. There we go. And C has two in series. All right. And the question is, rank the current. Rank I. Okay, from greatest to least. Alright, so just use Ohm's law, of course. Ohm's law tells you that the current is equal to V over R. Okay, so then find all the currents. Current, the batteries are all the same, they're V volts. And the resistances of each light bulb is the same, so there are ohms. And so the current is, let's do A. There's just one resistor, so IA must be equal to V divided by R. Okay. What about B? Well, B has two in parallel, and when you have two in parallel, the rec goes down. REQ is R times R over R plus R. Where when you have the same resistor and you have two of them, it's just half of it. And so we have IB is equal to the same voltage V divided by half the resistance. Okay, and you can see how it is 2 times A. And finally, in C, we have 2 in series, so IC is equal to the total voltage over the total resistance, which is 2R. This gives us half. Alright, so obviously half is the smallest, 2 is the biggest, and 1 is in the middle. Alright, next one. In part B, for the two, okay, so we're still ranking the current. It's just circuits are slightly different. Or no, A is the same. So this is part B of the same question. D2RT09. This is part A. Part A, Circuit B, and Circuit C. Part B has slightly different circuits. So here's part B. A and B are the same. A is battery, ammeter, light bulb. B is battery, ammeter, two in parallel. And C is the one that's slightly different. It's 3 in parallel. Okay. Of course, the more parallel branches you add, BCA, BAC, okay, thanks. The more parallel branches you add, the more current you're going to get in the system. So this is CBA. Okay, simple as that. Every time you add a new parallel branch, the rec goes down. And then when rec goes down, I goes up. All right. D2CT10. D2CT10. Okay. Current in a battery. A battery is connected to a circuit with two bulbs and a switch as shown. So it has a battery, and then light bulb A. And we're going back. The switch is between, so here's the switch. And then we have light bulb B. Oh, this is a classic. Right. When the switch is closed, closed meaning the circuit is on. Closed means that the drawbridge is down and the circuit is connected, and so the current can flow. That's what closed means. When the switch is closed, does the current in the battery increase, decrease, or remain the same? All right. So as soon as you close the switch, of course you get a new pathway, and when you get a new pathway, the current increases because rec goes down. Rec goes down. And so I total goes up. All right, simple as that. Let's do a side question. Chat, if you're in here. When I close this switch and allow the current to flow through B, what happens to current A as soon as I close the switch? What happens to current A? Does it increase, decrease, or remain the same? Ooh. This is a AP1 level question. So remember how, like in the FRQ questions, you're gonna get these part B and part C, where you, after analyzing a system, you have to change it up or something like that. Okay. And I'm gonna call time in 5, 4, 3, 2, 1. Incorrect. Current A does not change. Oh no. Yeah, current A stays the same. Why does it stay the same? Well, current A is equal to the voltage in A divided by the resistance in A. Notice how A is parallel to the battery, therefore the voltage in A is actually the same voltage as the battery. The voltage never changed. And the resistance of A is still the resistance of A, so the same voltage divided by the same resistance will give you the same current. Whatever extra current you're getting in the system, by adding that extra branch, that extra amount of current is going through branch B. The extra current goes through the new branch. All right, we'll get them next time. We'll get them next time. D2RT14. D2RT14. All of the bulbs in the circuits below are identical, as are all of the batteries. For the two items below, rank the magnitude of the potential difference. So now we are using our voltmeter between different points. Remember, voltage is the difference in potentials from one point to another. Okay, so let's see. Circuit A. Battery. Resistor. Resistor 2. Uh-oh. Baby's crying. We have two in series. M and N are between the first one. Over over here and over here. M and N. Here's V. Like so. And then B has 1 in series with 2 in parallel. Oh gosh, this is taking forever. 2. Okay, and C has 3 in parallel. Okay, 3 in parallel. Well, that's not very good. All right. So as I add more and more branches, of course, the current in the system goes up. If I did my current flow diagram, I can see how the total current is always going through the first resistor or the first light bulb. So I total is always equal to I1. All right. So knowing that, can we go ahead and answer this question? Greatest to least, rank the magnitude of the voltage drop. Rank V. Chat. Wow. We're ranking V, not I. We're ranking V. Knowing the fact that the total current is always going through the first light bulb. Okay, so if I have more branches, what happens to my total current? Okay, the total current increases all the time, right? The I1 in circuit A is less than the I1 in circuit B, because the I1 in circuit B is the total current, and the total current is more in circuit B, right? The I1 in circuit C is even more than the I in circuit B, because now we have 3 in parallel, and that's going to draw even more current. Okay, so the I totals are not the same between each circuit. The I total increases from A to B to C, and if I total increases, the V here is equal to I1 R1. R1 did not change. R1 is the resistance, and that's based on the light bulb itself. And so I1 keeps changing, right? Yes, very good, Emma. So C has the most total current, therefore C has the biggest voltage drop at the front. C, B, A. All right. Part B. In Part B, the circuits are different. We're still ranking the voltages. Let's see. We have a battery, light bulb, and then 2 in series with each other, which is parallel to the first branch. And we want to measure between here and here. Right? And of course, the battery is still V. This is circuit A. Circuit B has, well, it's the same setup except the dots are at different places. So you can imagine these dots are what your probes are connecting to. So recall that your voltmeter has little tiny probes, and so you're touching. How do we do this? How do we do this? There we go. whatever. Looks like a Game Boy. And this will give you your voltmeter voltage. This is your voltmeter. So you're touching these 2 points and trying to measure your voltage. All right, in part B, you have the same thing, 1 in parallel with 2 in series. All right, and in C, oh, the dots are here and here. Okay. And then C, we have same thing, except the dots are now in between. Oh, so it's in between the 2 here and over here. Should have used colors. Okay. All right, let us begin. One thing that could help us is Kirchhoff's, Kirchhoff's rules. But if you don't want to use all those algebra stuff, you don't have to. You can just simplify it using nodes and junctions and all that stuff. So identify nodes and junctions. You'll see that any region that you can circle, let's use a different color, green. Any region that you can circle that has no circuit element to it, like a resistor or diode or light bulb, is a node. So this entire region is a node, which means you can use the squeeze theorem of circuits and squish it into a point. We can also squish this region. This is also a node. Let's use the squeeze theorem here. And when we do that, you can see we have a dot. We have one pathway, two pathway, the second pathway. Okay. Essentially, we are touching the top of the battery and we're touching the bottom of the battery. So the voltage at A is whatever the battery is. All right. We can do the same thing in B. Notice how this entire thing is a node. Okay. So whether you're making the contact over here like you have in circuit A, or you're making a contact here, or over here where circuit B is, doesn't matter. All those points have the same potential because it's a node. So you can use the squeeze theorem, squish it. Same thing at the bottom. The bottom didn't even change. So you can use a squish theorem, boom, boom, push, squish it into a point. It's going to end up looking like circuit A. So the voltage in B is also the battery. You're touching the top of the battery and the bottom of the battery. And finally, in C, C is slightly different. C is slightly different. That's because we're not in the same node anymore. The bottom is the same. Here, that's the bottom of the battery. But we are starting from here after going through the first light bulb. So after going through the first light bulb, we've already lost a little bit of voltage. So this is going to subtract some amount of voltage. And whatever's left over is what we have across this thing. So if you use Kirchhoff's loop rule, so if this was V, or let's call it epsilon 1. Epsilon 1. This is R2. This is, no, let's call it R0. This is R1. This is R2. Okay. And we'll have our pathway going this way. You can see how epsilon 1 minus I1 R1 minus I2 R2 equals 0. In other words, epsilon 1 minus V1 minus V2 equals 0. Okay, and so V2 must equal the battery minus what you lost in the first one. Okay, so yes, Laser, you got it. A equals B greater than C. All right. D2WWT37. D2WWT37. Circuit with two resistors. A battery is connected to a circuit containing two resistors as shown. a student states, so it's just 2 in series, like that. This one is 4, this one is 6. So student states, using Ohm's law, the current is the voltage divided by the resistance. So when you have a bigger resistor, you have a smaller current. In this case, resistor B is a larger resistance than A, so it will have a smaller current. What, if anything, is wrong with the statement? Explain blah blah blah. Is anything wrong with this statement? Does the resistor, the 6 ohm resistor, have less current? Of course not. He is not correct. He's using laws for parallel. Yeah. The spelling of resistor, yeah, that's also not correct. Notice how the first one is incorrect, but they fix it. In the next sentence, it says, in this case, resistor B. So they do it right later. The current is the same throughout the whole circuit. Yes. So, but that is a statement that is true. What you need now is a reason, a law, a rule that will tell you that what you just said is true. So what evidence or what law do you know that you can use, hint, think Kirchhoff, that you can use to kind of justify your conclusion? Resistors in series. Okay. The way you justify is to use Kirchhoff's laws. No junctions, no splitting of I. Okay, you're very close. So that's essentially it. It's essentially it. It's just you just need to make a complete statement, a complete sentence out of that. So if you said something like, there's only one pathway, one loop in the circuit, since current does not split, the same current must be going through both resistors. Resistors in series share the same current, as nothing is split off, so that's another way of saying it. So all that is good. Or just, play it safe, just do a loop rule and write it, V minus V1 minus V2 equals 0. And then use a junction rule and say, like, from the junction between A shows that current 1 goes in and current 2 comes out, therefore current 1 equals current 2. So you can use the junction rule to justify as well. So there are many ways to justify it. All right, D2 LMC T21. Two resistors in parallel. Alright, so now we have R1 and R2 in parallel. For the circuit shown, identify from 1 through 4 how each change described below will affect the current in the battery. Ooh. So basically, whenever it says current in the battery, you're looking at I total in the system. And I total, of course, assuming there's only one battery. So I total in the system. And so let's run through this. In the first one, it says increase the current in the battery. Decrease. For the circuit shown, identify from 1 through 4 how each change described below will affect the current in the battery. Decrease the current in the battery. Have no effect on the current in the battery. Have an effect on the current in the battery that cannot be determined. All of these modifications are changes to the initial situation that is shown. Alright, so those are our options. Label A through D with I through V, scroll down. Yeah. So those are our options. Increase, decrease. So I is increase. I is decrease. And then triple I is no effect or no change. And 4 is cannot be determined. All right, so let's begin. A. All of these modifications are changes to the initial situation that is shown. Okay, the resistance in R1 is reduced. So if R1 goes down, what happens to I total? All right, so that's the question. So if R1 goes down, then does rec go down? And remember that rec in parallel, of course, the rec for 2 is always less than, the smallest resistor. So if R1's even less, then of course it's going to be less. But we don't really know what R2 is. So that approach doesn't really work. But in the end, rec does go down because the product over sum is now a smaller number. I total increases. All right, let's do B. The resistance in R2 is reduced. So R2 is going down. So same thing, right? R2 goes down, then the rec also goes down. And if rec goes down, I total must be going up. All right, now it gets interesting, C and D. In C, we have the resistance in R1 and R2 are increased by the same amount. All right. So R1 goes up, R2 goes up. And if you're going up, then of course rec is going to go up. And if rec goes up, I total goes down. D. Uh-oh. Let's have the chat answer D. In D, you have R1 go up. Oh no, sorry. R1 is reduced. R1 goes down. And R2 is increased. It goes up. So if R1 goes down but R2 goes up, does rec go up or does rec go down? Ooh. What happens to rec? Oh, we got some cannot be determined. We got rec goes down. Okay. Well, the problem is that we don't know. Yeah, but the problem is that we don't know what the actual values are. We don't know what the actual values are, right? So what if B2, what if R2 was smaller to begin with, right? Or do they start off the same? Let's see. For the circuit shown, identify from choices. Each change is described below. Yeah, I mean, it's R1 and R2. It doesn't say anything about them being the same at the start. We don't know what they are. Therefore, just because R1 is decreasing doesn't mean R1 is the smallest resistor. Okay, R1 could have been huge, like 1,000, right? And you can just go down to 999 and R2 could be something else, right? So technically R1 doesn't have to be the smaller resistor. Yeah. And if R1 is 999 and R2 went from 50 to 60 instead, and the smallest resistor is now 60 and not 50, okay, so now it's increasing. Right. So cannot be determined is the correct answer. Cannot be determined. Circuit with 3 resistors. Current. 3 resistors are connected to a battery as shown. They're all in series. Yay. 2 points in the circuit are labeled A and B. Is the current at point A greater? Oh, it's in series. I mean, is BO. It's in series, so series circuits have the same current. It's the same. Done. Talk about how there's only one loop. Make sure you try to use Kirchhoff's laws as much as possible when you're justifying. Alright, D2RT12. Simple light bulb circuit, 2 potential difference between 2 points. Rank the magnitude of the potential difference. Blah, 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 blah. Alright, let's see. D2RT12. First one, so we have battery. Here, let's draw it like it is drawn in the circuit. Plus is on the right side, so big line, small line. So this is A, and then B has 2 of them. And C has 3 of them. Alright, and the points in question, of course, across the first bulb, because there's only one of them. On the second one, it's right between, so here and here. The third one is between the third one. Oh, I didn't leave enough space. Oh well. Here we go. Alright, so the resistance are all the same, the voltage is the same. Got the same battery. Bulbs are identical. And then it's just a voltage drop. So the first one, there's only one, so it's going to drop all of the voltage. V1 equals V, whatever V is. Here, we have the same, therefore, we're going to split it up half and half. Okay, and finally, when you have 3, you're going to split it up into thirds. Right? So it's as easy as that. ABC. Okay. Now, when you have resistors in series, because they have the same current, if your resistors are different, because you have the same current, then the bigger resistor will drop more of the voltage, right? Since I1, which is the I total times R equals your voltage drop, so the bigger resistor will drop more voltage. But in this case, all of the resistors are the same, therefore they're in proportion. So if it's 1, it's 100%. If you have 2, then it's 50 and 50. If you have 3, you know, a third, and a third, 33.333%. All right. Second one has in parallel. So battery. First one is just the same. Okay, great. Second one, B, is 2 in parallel, and you're measuring the first one. Pew, pew, we're doing it here. And then C, you're measuring it on the second one. Now, of course, you should know that resistors in parallel have the same voltage, so it doesn't matter which one you measure, the first one or the second one. Okay, but B and C, even though B and C are the same, A is not the same. A is different. A only has 1. Or is it? Ooh. Well, just take a look at the nodes, right? Let's just do nodes. Look, this point is the top of the battery. This point here is the bottom of the battery. Over here, this point is the top of the battery. This point is the bottom of the battery. Over here, this point is the top of the battery. This one is the bottom of the battery. They're actually all the same. They all drop voltage V, whatever the battery is. Okay, with our nodes identified, we can use the squeeze theorem of circuits and squish it in. And you'll see that the contact points are essentially the top and bottom of the battery. All right, we are almost done. Oh my gosh, we have 3 more. Okay, D2 SCT36. D2 SCT36. We have a switch. All right. So battery, light bulb, switch, light bulb. There we go. This one's A, this one's B, this one's C. Hey, that looks familiar. Notice how A is at the bottom. It doesn't matter if it's at the bottom or the top. A is still in series and B is parallel to C. Only when the circuit is closed. 3 light bulbs and a switch are connected to a battery as shown. 4 students are discussing what would happen to the brightness of bulb A when the switch closes. Closing means that you drop the drawbridge and allow the current to flow. So currently, when the switch is open, you only have one pathway. It goes through B, and then it goes through A, and then you're done. But once you close the switch, now you have a second pathway that opens up, and some of it will go through C. Right? But eventually, whatever goes through B will meet up with what went through C, and the current in A never changes. It's still the total current, except for the fact that the total current has changed because there's less resistance in the system. Okay. So first one, Althea. Althea says, the current in bulb A has to be the same as the current in the battery since they are in the same branch. Okay, that part is technically true. The battery is going to put out the same current whether the switch is open or closed. Not true. So the current in bulb A is going to remain the same and its brightness won't change when the switch is closed. So unfortunately, the battery doesn't give you the same current. Even though it's total current that goes through A, the total current has changed because rec has decreased. When closed, rec goes down, I total goes up. Bertha. Alright, Bertha says, I agree. All that is going to happen when the switch closes is that bulb C is going to turn on, which is true, and is going to get half of the current. Whoa, okay. Bulb B, technically it's true because B is the same resistance, so it splits up 50-50. Bulb B only gets half the current as well, so it gets dimmer. But bulb A still gets all the current and its brightness doesn't change. Not true. Notice how bulb B was originally getting all the current, total current. So now it does split. So that part is at least true, but the last part where it says still gets the current and its brightness doesn't change. Unfortunately, that is not true. Cassidy, I think bulb A gets brighter. I think bulb A gets brighter. Why? The current in the circuit goes up because when the switch closes, the resistance of the circuit goes down. Since bulb A gets all the current in the circuit, it gets brighter. Yay, winner, winner, chicken dinner. When the switch closes, here's Dupree. Dupree says, when the switch closes, the resistance of the circuit goes up because you've added one bulb which has resistance, the current in the circuit goes down. Dupree basically says the opposite of Cassidy. Now, when you add a bulb in parallel, the resistance actually goes down, not up, because it's still a new pathway. All right, we're done. Cassidy is the correct answer. All right, the penultimate question. D2WWT38. All of the current from the battery goes through resistor A. Oh, whoops. A battery is connected to a circuit containing 4... Oh, wow. Okay, so I should draw it first. Here's our battery. Here's the first one. The second one in series with the third one. And then there's a fourth one in a parallel branch. Okay, so it's A, B, C, and then D. all of the current from the battery goes through resistor A. That's true. At the junction after A, this junction here, at the junction after A, the current splits up. Half of the current goes through D, and the other half is shared between B and C. So resistor A has the most current, followed by resistor D, followed by B and C, which have the same current. Yikes. What if anything is wrong? Chat, what is wrong? The first part is right. A does get all the current. But what is wrong? The current does split up, but how does it split up? Current takes the path of least resistance. Some of it goes through here, some of it goes through there. Doesn't split half and half. Yeah. So it's a 2-to-1 split. Very good. So 1/3 goes through here and 2/3 goes through the other one. All right, good job. So that'll change that. All right, the last one. 39, T39. Okay, we have a 24-volt battery. And then 2 in parallel in series with the third. 2 in parallel, series with the third. B, C, A. These are technically light bulbs, so I should circle them. There we go. B, C, A. 24-volt battery is in a circuit containing 3 bulbs as shown. A voltmeter across bulb A measures 18 volts. So we're saying that from here to here, if you use a voltmeter, it says VA is equal to 18. Right. A student states, since bulb B and C are identical, then they will each have the same current and the same voltage across them. The sum of the voltages across the 3 bulbs must add to the battery voltage, so bulb B has a voltage of 3 and bulb C also has a voltage of 3. No, that's not how it works. Remember, we can only take one pathway at a time. So if you take route 1, you go through B and you go through A. And if you take route 2, you go through C and you go through A. It's B or C, not B and C. So if you do your loop rule, you get 24 minus VB minus VA equals 0, or you get 24 minus VC minus VA equals 0. And this will show you that VB equals VC, which is equal to 24 minus VA. They're both 6. All right, that is all for tippers. Yay! So that's that. Put that in your 3-reading binder. Make sure your 3-reading binder is up to date. Tomorrow we'll play Kahoot, and then Wednesday we'll take a Canvas quiz thing again, but much longer this time. And then Thursday we'll start reviewing kinematics. All right. I'm going to close the stream now. I'll stay on. If you have any questions, go and type in chat. Thank you for tuning in. I'll see you next time.